mencari yang ada itu bagus ya. Kalau itu sih udah beli berapa kali
kecil banget tapi layarnya.
Untuk orang yang bikin perspektif infak.
kalau misalnya kalau berapa itu nggak tahu yang untuk
Itu yang perlu pengeras suara. Ini baru ada komposer. Oke, saya oke. Ya, free to
Tulisannya
kelihatan.
agak seni gimana?
Well. Mentok.
Gak kelihatan tuh sini. Oh.
Well.
Karena bagus.
Tulisannya nggak kelihatan. Hah?
Nama dia kan Stella, kayak Tesla. Tesla. Oh iya.
Jadi suka dipanggil Tesla gua.
Ini kayaknya untuk recordingnya bakal ada masalah deh, karena nggak kerekam agak. Gua lupa bawa kamera soalnya.
Oh, bawa.
Iya.
Apa lagi?
So, hah?
Pakai HP lain?
It's hard. Betul, biasanya udah itu overheat baterai. Betul.
Halo guys.
Soft filter.
Itu belakangnya lucu.
Oke.
Jadi yang dulu. Iya, saya. Oke, itu kan.
Okay. So, thank you for coming. Previously, we have talked about database, and right now, based on the popular demand, I will talk about Java concurrency. But please, I'm sorry before, because last week, even during the weekends, I'm feeling a bit unwell, so doesn't prepare a lot of materials. But the other hand, because the number of people actually in this room is not much, so maybe we can have more two-way discussion instead. Okay? So let's talk a bit about Java concurrency. Why Java? Simply because most of us in our tech stack is using Java. Actually, we can also talk about concurrency in Go or the language like POSIX-based concurrency using C, but I think the topic will be too broad. So let's focus on Java. So before we start, I would like to know how many of you that at least already playing around with concurrency in Java. Kenny, be honest. How over here? Daniel, Artanto, of course you have to, because if not, workload cannot run. Yeah. So, but many times actually we deal with concurrency in Java because of one, Traveloka is using Java, and second one is for the server, for the backend services, having multi-threaded process as a Java process to receive the request is kind of the normal one compared to Node.js, for example. In Node.js, usually there's only one. Oh, it's not usually. It's always only one thread. Always one thread, and usually, if you would like to utilize all available processor in the server, you actually spawn multiple process that is independent to each other, and monitor that using kind of I forget the name in JavaScript. Sorry?
Yeah.
Yeah, like a TM2. Yeah, like a monitoring the processes. So it will spawn multiple processes, and then this process basically only has one thread. But in JavaScript, it's quite special that normally we program in asynchronous manner. So even though only one thread, but seemingly able to respond to multiple requests concurrently. Always actually only using one thread. That's using JavaScript. But the other way around, like Go, Go is maybe the other extreme, that having Go routine is very cheap. That you can actually spawn millions maybe, depending on your machine, of concurrent Go routine. That is very lightweight. That doesn't always actually create operating system threat. That it's Go routine that actually kind of having its own, but correct me if I'm wrong, having its own context. So it's kind of very lightweight thread. So that is Go. A bit, and Java is actually a bit in the middle, where usually on GVM implementation, the Java thread actually corresponding to one-to-one to operating system thread. Usually in most of the implementation, but I think not always, but usually like that. And in Java, we usually using thread pool, and then there is kind of a built-in or internal queue that if you actually put runnable into the executor service, it will be queued. I'm not sure about the exact implementation, but most of the Java implementation that I know is having kind of a thread pool queue. So the runnable will be queued to be executed in the thread pool. Is it correct or not? This if there is or it's not something like that in Java 11 it's different. Okay, let me know. Because for me usually using less than Java. Okay, so what is the reason for concurrency? Just looking a bit back to the theory. Scaling sequential processing is limited to the fastest single-threaded processor. Basically, physics is dictating the single-thread performance limit. In the past, that we're trying to have a gigahertz race that having single core as fast as possible, but turns out it become too hot. Simply because of physical limitation, and also it's speed of light limitation. That having kind of unlimited speed in a single core is kind of impossible, physically impossible. And that's for the sequential processing. And also, strictly sequential processing is inefficient use of scarce resource, especially in modern processor. That getting 2 cores is basically very minimum for the lowest kind of the lowest grade of CPU right now, and usually it's 4 to 8, sometimes 12 for server core, and even for mobile phone it's usually 4 to 8 already. So using concurrency is basically utilizing all the core because it's not kind of automatically, the load is automatically into multiple processor unless usually you run multiple process or multiple program at the same time. And also waiting for external events and I/O to be completed. Okay, so imagine that we actually call third-party services. For example, just calling third-party API, and our process actually call the API, like let's say opening the port and then send the HTTP request and waiting for the response. If we only use one thread, what will happen actually? Waiting until, yes, and it might be maybe half second, 1 second, or if airline API maybe 20, 30 seconds. And for the time, then basically, if there is no other processes, then the CPU is idle and not processing other requests that coming to us. For strictly single thread synchronous process, will be like that. So it's like waiting for the result. And also like writing to this or reading from this will be like that. Reading from this maybe for current SSD maybe 10 millisecond or even 1 millisecond, but still 1 millisecond is about maybe 1 million CPU cycle already for the normal CPU, for the common CPU. So Then it's basically resource being wasted. And the last one is simplified modeling of algorithm. Imagine that the code that we write for requesting for the server response, we wrote in such a way that we actually writing by our own the logic to do multiple things at the same time. So like maybe we actually having busy wait or calling to the request, and then getting for this request to be returned, and then at the same time, if there is no response, then we do something else and so on. So it's like actually, if any one of you actually try game programming, whatever, it's like a domain game loop, and then that's kind of do this. If not done, then do that, and so on. That's basically quite complex. So if we actually using concurrent support on the underlying virtual machine or underlying OS or underlying programming language capability, then basically simplify the model instead of we try to model everything by ourselves. Okay, what is the difference between asynchronous and multi-threading? Anyone of you used to write in JavaScript? JavaScript, anyone? Okay, one. Any? JavaScript? JavaScript is usually single thread. At least every website single thread for now. But it is usually asynchronous. Well, it's true that initially it's actually meant for the web browser, which is GUI is usually asynchronous in the first place, GUI. But even for the server-side JavaScript, it's usually asynchronous. At least people using non-docking I/O or that's basically the default choice. You write a callback code and then you pass the function, and then when the response comes or when the file read successful, then the callback code is called. That's asynchronous. So basically, like I'm saying to Daniel, help me to do that. After that, please come back to me. That's basically asynchronous like that. It is about the task. It's not about the worker. Maybe Daniel is the only one that is possible to actually complete the task. There's nobody else, that's Daniel. After that, Daniel must do that again. Or Daniel must do something else. And after that, come back to me. That's kind of asynchronous things. Maybe Daniel can ask someone else, like for example, calling external web server, and then come back. But still, only one worker, which is Daniel. That's asynchronous. Different from actually having multi-thread. Having multi-thread, for example, like one, let's say we have 6 core CPU. So those 6 people over there, everyone doing different thing. One is maybe writing, the other one is reading, the other one is just sitting idle, the other one is basically trying to kill himself or whatever. Yeah, that is a multi-threading. So that's different. But on the day-to-day, it's actually we use both. Especially in Traveloka, if you see on the backend code, that actually we kind of a bit strange actually, but kind of try to fit asynchronous pattern within our Java backend code. So, anyone of you actually working on things outside BP, outside DBA, that a lot of callback. NTID, for example, or backend services. There's actually a lot of callback code. And with that callback, we actually, many times, it's actually remote callback. So we call remote function, and then after it finishes, the response will trigger the callback. So if you actually see on the stack trace, it's kind of confusing because the the caller stack doesn't appear on the response. There is no whiteboard here. Okay, so for example like this, maybe I would like to Kenny and Stella and Kyle. Help me, help me, help me, help me. Yeah. So imagine that. Okay. So the program pointer, I am the program pointer or the instruction pointer. Okay. And Stella is the thread that actually do the calling. Mikhail, maybe you can go there. Mikhail is the web server. Maybe flat booking service, and Kenny is the other tab on the calling service. So for example, like the current state is we go to the, for example, get flat booking. Okay, get flat booking, and there's a callback. Okay, get flat booking. Maybe the ID 123. Okay. So right now, get flat booking here, and then we determine that the server is Mikhail. So I go there. This is the instruction pointer actually. Okay, please give me flat booking 123. Okay. After he gave me the flat booking, and then I will go back. I might not go back to Stella actually. I might go to the other side. This is Kenny. Okay, here's the flat booking 123. Okay, see the possible problem. Kenny maybe can say, what is flat booking 123? I never requested. So this is actually the one that happened right now. So how do Kenny now that there is booking 123 being requested and there is a response for that request? How do you know? Maybe you are
I really have to know that the response is actually for which request.
Maybe, for example, so the sequence of the program is this: get flat booking 123. Then after that, get the destination of the booking 123 to trigger for the ticket with this airline. Okay, but that information is not transferred to me yet. Okay. So how do you know how to process the response?
Using callback. I'm
Yes,
using callback, but how do I know
Yeah.
that one?
How do you know?
How do I trace back the response comes from which request?
Yeah, that's the key. You will know because both of you actually share the memory. So, for example, there is a request from somewhere else, maybe from ERP user. Okay, maybe from ERP user. Okay, there's a request. The request are handled by this type, but the request actually stored in memory, right? And that same memory can be accessed by you. Okay. In our code base, usually it's in form of closure. So actually, kind of wrapped within the callback line. So that's why many times you need to add final keyword. So final keyword, that means that this variable is put into kind of a local. Yeah.
When you transfer from it to stack, right?
Yeah. So you put it into stack actually.
Yeah.
Yeah, into stack. But then the stack itself might actually, it's not really stack, it's more on, Java is OOP language, right? So it's put into the callback object itself. So it's put into a field within the callback object. And that callback object is accessed by Kenny when he got the response. So there's a, okay, maybe imagine that there is a callback object here, and then you call Mikhail, this is the callback object, and then the response comes, and the callback object is now accessed by Kenny. How? So this is actually the magic within our system. There is actually a correlation code. So if you actually open the JSON RPC, there is a request correlation ID. So this how Kenny can actually find the correct callback object. So actually, maybe the rest that talk, we can discuss about how it's actually being implemented by our Mahaguru Denny. Yeah, it was even by the himself. So the correlation ID actually to find out which callback object to be accessed.
It's the same with JMS correlation ID.
Yes. So if you actually do debugging on our RPC call, you can see the correlation ID. And that correlation ID is the magic to actually for the entire stack trace if you want to combine the stack trace. So because it's different thread, you have stack trace, but it's done already, and then maybe you are doing something else, and then go to Mikhail and maybe some error happen. You need to check on the correlation ID. So in Mikhail, there's an error clock, and then the response comes to the caller, and then the response is basically error, and then in the caller actually also throwing the stack trace. Then how to correlate using the correlation ID?
So the correlation ID is sent with the request.
Yes.
And then the response also has the correlation.
Yes. That's the key actually. Okay, that's a bit Traveloka specific, not just even Java specific, but even actually Traveloka specific. Quite rare for us. Why? Actually, this is kind of an intentional decision that is being took by enterprise when we actually building the DP and TPI and so on to not using asynchronous. Right? Why? That's question. Okay, you can move. Why? Here. Let's see on the use case of why we have asynchronous call in the first place in Traveloka. The asynchronous call in the first place in Traveloka is used for the call to the third party. For example, airline or payment gateway, or maybe whatever hotel booking or whatever. That the response might come even up to 6 minutes, 5 to 6 minutes. I saw the order very slow. And for payment, no. Actually, it's most used by flight search actually. Mostly used by flight search. See on the progress bar when actually we do the flight search. That actually behind the scenes, we actually create tens, maybe hundreds of remote call to flight search machine, and then from flight search machine to the airline. So just multiply the things. So let's say that we have 1,000 concurrent user, and every user spawning maybe 100 call to the flight search service. So it might be 100,000 concurrent requests. That's only if we talking about 1,000 concurrent users. What happens if we actually have more than that? And then times how long it takes. Flight search can be about 1 minute, 2 minutes, even more. So 1 minute for 100 concurrent 100,000 concurrent requests. So it's already 6 million concurrent requests active. Imagine if we actually not using asynchronous, and every single request actually represented by one thread. So we have 6 million active threads. Good luck. I can show you maybe after this kind of short demo about having the impact of having multiple threads in the system. Use Java. So that's the reason.
Why?
Okay.
WordPress doesn't use
Okay.
synchronous?
That problem doesn't happen in the past. So the problem doesn't happen in the past. So most of our problem is related to database call. Database call is even 100 milliseconds at most. Many times it's only 10 milliseconds, 20 milliseconds. And the trade-off of having unclear code path and debugging that kind of a crazy stack trace and so on, compare that into just using synchronous, but with multiple threads, is actually better to use synchronous with multiple threads. Because even in the current state of the system, let's say we have 4 gigabytes of RAM, for example, and every thread usually allocate like 2 megabytes of memory. So we have how many? 2,000 threads active. It's okay. 2,000 threads active is okay. And if every request is written within 10 milliseconds and so on, well, actually, even though we have a lot of concurrent requests at the same time, but because every request is served quickly, still the trade-off still move towards the full synchronous system. It's easier for the engineer actually. Easier for the engineer. But then how about, for example, long-running process, like generating emails? We have API, right? We have TBI that actually generating emails. That can be slow. That can be slow. And actually, requests to backend system can be slow. So, what are the alternatives? Basically, asynchronous, in essence, is basically callback. So for that, actually, we think either we use workflow because it's basically callback in the first place, maintaining the process in the database because it's very long. It's actually for long running process. It's actually for long running process. Better to persist that actually in the database because it may be continued later on. If we actually keep that in memory and then the process or the process actually die, then we have to restart from scratch. But if you put in the database, we can continue. That's for the workflow use case. And the other use case is having explicit callback. Explicit callback, for example, I think right now there is no. Even we still not needed for it. Salesforce, are we using actually explicit callback?
Sure.
Not sure. Even there is no use case for us right now. For that.
Salesforce calls our API, but
No callback.
we don't call them.
I see. Yeah, so even the use case is not there. That we have millions of concurrent requests, that every request might spawn more than 1 minute. Is there any use case, such use case in our system? For now? I don't think so. Actually. Yeah, but that's one reason. So just want to simplify. Because using purely asynchronous is a bit hard and many times actually very hard to debug. But it's fine actually if you would like to use the asynchronous, but just be aware that even if you read the stack trace, you'll be surprised that the tunnel stack basically stop at JD thread. That actually receiving the response. That's it. There is you don't know who call it actually until you actually try to find the correlation ID and then find the original object with the same correlation ID. It can be like that. Okay. Is that answering the question?
Yes. Yes, but for performance perspective, usually for asynchronous query, the
Mhm.
system is more resilience. It's more stable. I mean, like if the one that call our API doesn't meet like strong consistency like the writes, then if you're using the asynchronous for query response, it's more resilience.
For the caller, yes. For the caller, true. For the caller. So if we actually call external things, it is recommended to have it. Better for us to that. But if we actually become the server, not always. Not always. If we call external things, yes. But if we become the server, not always. But yes, there is an abstraction link actually. There is abstraction link. The way we build the RPC proxy. Actually, the server and the client need to follow the same pattern, whether asynchronous or synchronous. Either both become synchronous or both become asynchronous. This is the thing that I don't like about the Terracotta Java stack, because it actually force you, if you use using RPC, Java RPC that we use right now, they're basically forcing the client and the server to use the same pattern. But I'm a bit, basically to make the decision a bit egoistic, where because we are mainly become the server instead of the client, then okay, we only support the synchronous one. If you would like to use the asynchronous one, please implement by yourself. Yeah, but that's true. If you call external thing, better for us to be asynchronous. Is it answering the question? Yeah. And yeah, usually during the board. So there is a diminishing return on CPU versus IO heavy thread. So this is basically kind of rule of thumb. Actually, I did this as part of my undergraduate thesis. That for the parallelism, the limit of parallelism for CPU heavy thread. Actually, when we close to the number of the worker or the CPU, that's basically the most optimal. Become kind of the most optimal utilization. So we can use most of the CPU, but not incurring heavy loss from context switching, and still having quite predictable running time for every process. But for I/O, after this I will like to show you that for I/O thread, actually it's fine if we have a lot more threads than the number of CPU, as long as you still have sufficient memory. Because internally, thread is actually implemented quite more or less a bit similar to the one that we discussed about the callback and so on, but nicer implementation. Why nicer implementation? When we do the context switching, actually the entire stack and the pointer, which is not correlation ID but the pointer to the last instruction and to the next instruction, is actually kept into the memory. So the entire working set actually in Java, that's basically usually the JVM. The stack itself actually put into the heap, and well, that's it. So when it being called again, and then it's being put again into the active memory. So as long as you have sufficient memory, that's fine. That's what I thought. If you find something else, still you will let me know. But for the current situation that we have actually very large memory, usually like 8 GB, 6 GB, and so on, having a lot more threads compared to the number of CPU doesn't matter. As long as it's I/O heavy, not CPU heavy. If it's CPU heavy, then much more. So, where is this thing? Can you see this? Is it okay? Or still too small? Oh. Okay. Okay. So I have one CPU process. This one's very simple, only giving a lot of load to CPU. So we can basically calculate some trigonometric heavy stuff. So only one thread. I have only one thread, and if you see on the CPU utilization, sorry, where is it? Okay. Basically 99% of CPU, which is not fully utilizing the entire 4-core CPU. And a bit slow, like this. But if I use 4 thread or 8, the number of CPU, that basically is much faster. Because see, 600% of CPU. Okay, this is actually 8-core machine. There is a Google Chrome helper, so I think Google Chrome take quite a lot of CPU. But at least we can see that it is actually much faster because we are using the entire set of CPU, and it's as well getting hot. I think it's too many. Only 1024, so not too many. Okay, 71 seconds. What is? If we actually run it using single thread, it will be about 8 times from this. But what happens if it actually IO heavy? This is CPU heavy process. How about for IO heavy? Still slow. Still slow. Because I have a lot of things to be done. I have 1024. But let's see if I have more thread. What happens if I have 128 CPU heavy thread? It is more efficient actually than having only 8 thread, but not much. Not much. Why? Because I only have 8 core. Because I only have 8 core. A bit efficient, a bit more efficient. Maybe can handle about 1 core more efficient. But still, in overall, it's not much faster. And let's wait until it's done. And you can see for every single process, it's actually getting slower. For every single process, getting slower. Because the number of threads, actually, the operating system will try to have a fair share of the CPU across all the threads. But yes, at least we can get 10 seconds better. But for the IO heavy, it is way better. Eight seconds with 128 thread. What if I go with 1000 thread? For CPU, will not be much better again because I only have 8 core. It will be about 1 minute. But see, even the first result getting slower because basically everything seemingly runs in parallel. So the operating system actually handle all of the scheduling for the thread to more or less getting fair share of the CPU. But then suddenly the result will come. Yeah, well, because every process is more or less same. I'm just calculating multiple trigonometric functions. So it's same complexity for every thread. So that's why the result will appear more or less in the same time. But every process took about 40 to 50 seconds. And in total, still 61 seconds. But what happens if it's IO thread? Boom. The entire process less than 2 seconds. Less than 2 seconds if it's IO thread. So having more thread for IO, not that problematic actually. Not that problematic actually for the current generation of CPU plus memory. But still there's a limit. What happens if I create 8,000 threads? Every thread is about 4 megabytes. What happens?
Explode.
Sorry?
Explode.
Yeah, maybe exploding with thread pattern. What will happen? I have 4 megabyte per thread. The default stack size I think 4 megabyte, and I would like to spawn 8,000 threads of memory. Let's run. Oops.
I think there was a
I saw something, and it's not completed actually. It's not completed. Actually, it's still running, but no result. Okay, let's scroll. What happened? Uh-oh. Out of memory error, unable to create native thread, possibly out of memory or process resource limits, which it needs. And it's not actually finished. So this is actually the danger of venturing into concurrency. If we are not careful, and if we hit something, maybe because of memory, or we actually create an exception in the exception within the runnable, this will happen. Or this usually happen. Your process hang, there is no result, somewhere no response, and suddenly stop like this. So this is actually the danger of having concurrency in place. Even I would like to show you. Okay, let's make division by 0 here. It's still compiled. How to make it not compiled? And how to make it still compiled? Oh, you know. Okay, it will compile. Okay, but it will make division by 0. Okay, let's run. Okay, 8 thread is second. Run. Okay. Sorry, it's not division by 0. No. Because it's the data type is double. Okay, sorry. Just make it. Okay. Okay. Sorry, this is not to be followed, but just for sake of example. Okay, where is the error? Where's the error? It should be like division by 0, right? Or if I copy this to somewhere. Let's see if I put it here. Okay, let's see if I put. Okay. Should be something like this, right? Division by 0 error. But why? Why? There is no exception. Although clearly this is a division by 0. What happened actually? I'm not sure whether it's Java specific or not, but as far as I know, Java is like this. C also like this. If the thread, the other thread which is not main thread class, the exception is not caught everywhere. Why? Because every single thread actually has independent execution pointer. that is not impacting each other. And somehow, I don't know why in Java is being implemented like that. On the runnable, basically the top level runnable, there is no such thing as kind of a top level execution top level exception handler in Java like that. There is no top level exception handler on the thread that you spawn. That is only on the main thread. I'm not sure why it's made like that. I'm not sure. But at least in Traveloka, if you use the backend building block from backend team, on the top level runnable that is spawned by their own executor service, there is a kind of top level try catch handler. So if you don't have that luxury, usually where is it? If you don't have that luxury, usually on the top level runnable, where is top runnable? Where did I put it? Oh, here. Here's the runnable. Usually, very simple way to fix it. On every top level runnable, usually I just put try catch here. And then just maybe like print the stack trace here. So after that, well, now we can see it. And see, it's not related to the main thread. This is actually stopped on the Java thread API, thread library. It's not to the main thread. So this is Java. Not sure about Go, not sure about the language, but in Java, if you forget to put top level try catch handler, and there is exception in your thread, there will be no result. There will be no exception appear everywhere. Yeah, that's Java. And let's go to the next one. Okay. So, but when do you use asynchronous? Actually, this is answering your question. There's a when you should use asynchronous when you don't want to reserve the system level resources for thread. Not wanting a thread to be blocked waiting for something, and when you don't mind reading complex stack trace. Anyone like to do front end? Why? Yeah? Okay. On front end, okay. What did I talk past? Okay, when you don't mind reading complex trace, if you actually have experience in working front end, that you put usually callback everywhere and closure everywhere, very hard to actually read the stack trace, especially if you have very deep level of closure and you would like to find the value of one variable. Usually it's like a scratching your head. What is the value of this variable? Simply when you forget to put this select this dot x or whatever, simply forgetting that will lead you to nowhere. That's asynchronous. Okay. So actually, I have one more topic actually, but I haven't put any slide. Actually, this is the hardest thing of the hard thing, is how to test concurrency. But I'm not sure because one of the co-founder would like to use this room, and I also haven't prepared sufficient materials for how to test concurrency. I would like to show you how it's usually being tested. Actually, if you would like to open our backend repo, okay, just want to give you the pointer. If you would like to open our backend repo, you can find on the testing for most of our backend stuff, and including the one in subledger, the banking. Actually, there are there are a lot of concurrent testing.
This always fail. This will always fail.
Really?
Yeah.
Yeah. So the key of testing of a concurrent system or concurrent programming, the key of the test is first you need to simulate the possible what if condition. So simulate like this. What happened if your thread actually failed? So you need to introduce failure to the method or to the things that would like to be tested. Okay, you need to introduce failure, and you need to actually test it using thread pool which is more than one. You need to test maybe 4 or 8 thread pool, and also test it using the number of thread pool that's more than your CPU.
What's that?
More than your CPU.
Why?
Why? Because when everything happen in parallel, okay, the number of CPU more than the actual the number of thread. You can see about the performance problem. If it's CPU heavy, okay, if it's CPU heavy, it will hit kind of the wall. If you actually the number of thread more or less same with the number of the CPU. But if it's I/O heavy, it will still going well.
You always I/O heavy, right?
Yes.
CPU heavy, right?
Yes, but that's why test it using the number of threads more than the CPU to actually really check the condition when you have the optimal scenario, which is I/O heavy, not CPU heavy. And there's one thing, deadlock. Deadlock highly likely to happen if the number of threads actually more than CPU. So like this. If the number of threads actually less or Well, no, sorry. Sorry. No. For the Java, no. Actually, if you even more than have, even if you have more than a number of threads more than CPUs, still same. Sorry. It's not relevant. Sorry, it's not relevant. Sorry, it's not relevant. The talk will still happen against us. We still happen against us because the OS scheduler will still schedule the regardless of number of threads. Sorry, it's not relevant. Yeah, but you need to check that to make sure that your data is actually IO heavy, not CPU heavy. Because if it's CPU heavy, only in some cases actually it's relevant. But again, within our backend system, usually IO heavy. That's why that the number of threads more than the number of CPU. And there are other cases that we need to. So there's no slide for this, but this is based on the experience of having debugging a multi-threading system, Deadlock happen if you are not careful. But usually deadlock only happen if you at least a bit careful. Why? Because a lot of people didn't realize when you actually go into concurrency, you need to have some sort of locking in place. If there is no locking in place, there will be no deadlock. If there is no locking in place, there will be no deadlock. But your program will fail, usually, of the shared state. So remember on the shared memory between the threads, if at the same time there are more than one thread accessing the same memory area, what will happen? Not always. I really wish that I have whiteboard here.
Inconsistency.
Right?
Inconsistency.
Yes. So again, maybe Kenny help me.
Can you know what that?
Okay. Can you help me? And Stella, help me. Okay. I am variable X. Okay. I am variable X. Your task is same. Your task is X equal to X plus 1. Okay. Let's start from 0. Okay. Repeat that 3 times. Okay. I am variable X. Okay. So this is the first scenario. Only one thread. So Stella, do the operation. I am variable X.
1, 2.
No. Ask me. So, okay. X equal to X plus 1. So, right now X is 0. No. Ask me. I will tell the variable. I will tell the value. Okay.
What is the X?
0.
What?
Yeah. Then
What is the X?
1,
2. What is the X?
2.
X is 3.
Yeah.
What is the X?
I think you mean like what is X and then you answer 0 and then I set X to 1.
Yeah.
Like that.
Okay. Better like that. Okay. So initial state I'm 0. Then you add 1 to me.
What is the X?
Right now 0.
Okay, start 0 and start X to 1.
1.
What is the X?
1.
Set the X to 2.
2.
What is the X?
3.
Set the X.
Okay, that's all. Okay.
CPU clicks.
Okay. Show me. I'm 0.
So what is X?
0.
Set X to 1.
1.
What is X?
1.
Set X to 2.
2.
What is x?
2,
Set x to 3.
3,
What is x?
3,
Set x to 4.
4,
And so on.
yeah. So like that, right? So if you ask me to that again, you do this. Okay. Now both of you try to do this to me at the same time together.
What is the x?
0,
What is x?
0,
Set x
Set
to
x to
1.
1.
1,
Set x to 2.
2,
What is x?
2,
What is x?
2,
Set x to
What is
3.
3.
What is x?
Yeah, okay. That will illustrate the problem. So I'm the shared memory. There are two threads trying to change me at the same time. Okay, that's just big problem in multi-threading actually. So imagine that if you set x equal to x plus 1, the first step is you need to ask x what is your current value. Then add 1 to the current value and then set x to the next value. So there's actually multiple steps, not single step. Not single step, it's a multiple step happen. If there is more than one thread doing the same time with x, the result will be messed up. Right now, I would like to introduce locking. So, when Stella lock me, I would like to answer only to Stella. Can you ask me? I will not say anything until Stella unlock me. Okay, you do it 3 times, you do it 3 times. I'm 0.
What is x?
0,
What
Set
is
x
x?
to 1.
1,
What is x?
1,
Set x to 2.
What is x?
2,
What is x?
What is x?
2,
What is x?
Set x to 3.
3. And then
What is x?
3,
Set x to 4.
4,
What is x?
4,
Set x to 5.
5,
What is x?
5,
Set x to 6.
6. Okay. That is the beauty of locking. Okay. Actually, locking actually there are more than one way to do locking actually. This is optimistic lock. Optimistic lock means that if I'm not answering, this is fine. You just try to get and return to him. But there are other kind of lock that actually like he will wait. You cannot do anything before I answer you. So what happened if Stella is not yet complete? Then Kenny cannot do anything, just waiting for me. Kenny will idle, waiting for me, and will be totally different if we have 2 variables, x and y. If, for example, to read x, I need to ask y, and at the same time, y is being locked by Kenny. But Kenny is waiting for x. Stop. Stella will stop, Kenny will stop. R2, stop. So this is basically the idea of locking in multi-threading scenario. That will not appear if usually will not appear if the CPU only one. So there are cases that even though it's multi-threaded, the result is still correct because somehow depending on the scheduler, depending on the VM, depending on the OS too, because of the CPU is one, there will be no actual concurrent asking about X. Because even though you are on different thread, but for you to call me, you need to wait for her to be done. Because only one CPU. So depending on the OS, but why depending on the OS? Depending on the VM, depending on programming language, because there are cases that even though it's only one CPU, it's kind of even more than 2 or time slicing. So even though Stella is not complete, Stella will basically halt in the middle somewhere and then you continue and so on. So depending on the CPU, depending on the VM, depending on the programming language. So that's why you need to test it actually on the actual multi-threading system. Not just test it on one CPU using VM. Sometimes it's not really uncovering the problem. And don't forget to push the error. Okay, thank you. Thank you. So, I think that's the materials that I would like to cover. Sorry for the last one, I don't have any kind of preparation beforehand. Any question? Yes.
I actually have some questions about the Java threads.
Yeah.
So you mentioned that in the OS they will do time sharing, right?
Yes.
The process, right? In Java thread they don't do that. I just want to know that.
Not sure. I think also depending on the GVM. But for the GVM that we use, like the normal OpenJDK, I think actually Java delegated fully to the operating system. Delegated fully to the OS.
So let's say we have a thread full of 8 threads.
Yeah.
And then we send 32 tasks
Yeah.
to be done there.
Yeah.
Is it the 32 tasks will be done concurrently or just
No.
8 tasks?
Only 8.
Only 8 at
Only
a time,
8.
right?
Yeah. So okay. So the question is more on the how about the executor service, the Java executor service. Java executor service, there's no time sharing. So the 8 thread will still run as 8 thread. Even I would like to show you this one again. Okay. Okay, so the IO heavy, we have this IO heavy, and the full size is 8. Okay, full size is 8, and we have 1024 tasks. And let's execute this. Only 8 at once. 8, 8, 8, 8, 8, and 8. So, although it's actually waiting for I/O, it will stop. Java will not schedule unrunnable in place of the waiting time. The thread actually half. Sorry, not half. Sorry, the thread actually waiting. Sorry. When we talking about multi-threading, we need to be careful on the word choice. Half and waiting is different. So basically, the thread will wait for the I/O. For this one, the I/O is a timer. It will wait. Will not suddenly the other thread actually get it. So that's actually the reason, also one of the reason why we can schedule more number of threads than the actual CPU. So to make use the available speed, can really make use of the available CPU. So like this. The other one. 128 at the same time. Because Java actually released the control of the actual scheduling to the operating system. So the thread pool says 128, and out of the 128, how it will be scheduled depends on the operating system. At least for the OpenJDK is like that. There are the other JDK that's not like that. The embedded one, that's what I know. The embedded JDK. Yeah. There are 4 embedded devices. So if you work in embedded devices, there are JDK with home OS. So directly JDK to hardware. So for that one, it actually scheduled the thread. At least for us, we are tossing that one. Yeah, but there is. Any other question? Good question. Thank you. Any other question? No. Okay, so if there is no other question, I would like to let you know that several other things that is not basically discussed here, but you need to consider when you're actually doing something with concurrency. Is you also need to consider. So I will not go into the details. You can read the books about that and so on. But one of the consideration is how we actually deal with the inter-thread communication. Inter-thread communication using locking is one of the things. This one example, but that might not be the most efficient way. There are other inter-thread communication that depends more on the queue, for example. So first in, first out, simply first in, first out, using kind of pipe. Even it's actually useful for inter-process communication, not just inter-thread communication. So there's no locking. So just like streaming all the way. Yeah, maybe if you deal with a high performance or time sensitive system, we'll go to that, but I'm not sure. I think for our use case, there is no real apparent case, but in the past there are cases when we actually too aggressive in locking. So in the past there was cases when traffic actually down when we were too aggressive in locking. So even though the entire jetty is asynchronous, so the entire backend service is asynchronous, even in Infrastructure total asynchronous. We have even hundreds of threads for IO bound system, but there are a lot of synchronized keyword that is on the class level. So synchronize this. That basically effectively making the entire system become single thread. What an effective way to use asynchronous? Single thread synchronous. So the entire service becomes single thread synchronous. So although locking is kind of safe, but don't overuse, become like locking the entire service into one single thread synchronous service. Usually we can be more granular in locking, like using specific variable to lock or using a specific object to lock. That is preferred. Or if we can actually really make use of local variables, so there is no sharing of variables between thread, no sharing of memory between thread, you can actually let go of locking at all. Maybe in some cases on the IO wires or like for the heat map, on the hash map that usually like a share between the thread for lookup or something, you need to use lock. There are cases when you can do kind of an extreme bit, although the memory is shared, but you can actually let go of locking, is when you actually share it for read only. But still need to be very careful on the first initiation. If the first initiation is happen within multiple thread, goodbye. But if it fully read only, you can actually let go. But not recommended. That's usually for adventure soul, no locking at all. Or if it actually asynchronous, if it only actually for it only, you can use Java concurrent data structure that actually can handle that. Or you initiate that within one thread, and then you make kind of a copy of it, make a copy or make into immutable data structure. That will be helpful if it is immutable. But if it's mutable, without locking, good luck shooting your own foot. Usually that kind of, it works on my local machine but broken in production. So that one need to be really careful. And also, what I haven't really discussed, maybe we really encounter that. But if you do game programming, maybe it will be very useful about the priority, like a background, low, medium, high priority thread, and so on. Usually for I/O as in keyboard, most input is higher priority thread. Also need to consider trading is single process, still within the same process, not different process. So if you have like global variable and so on, it will be so don't forget about it. And need to also consider the context switching cost. The context switching cost when the OS need to swap in and swap out the local variable of the thread, that need to be considered. But most of the time, it will be safe. There is no kind of a dark magic in multi-threading or concurrent programming, except on how the way you actually need to find out the best locking strategy. That's sometimes kind of a dark magic because it's very hard to test sometimes. And need to imagine how it will interact to each other. Sometimes we simply forget, and suddenly, like that, what race condition happened. We thought actually we'll get 10, but turns out we only get 5 or so. Or when we thought we are actually using multi-threading and concurrency, actually we locking it to extreme into effectively become single thread and synchronous process. Okay. Anything else? If not, then maybe for homework you can take a look on several of the books, Java Concurrency in Practice. Also, you can see on some of the test cases that we have in our Java backend code. And also recommended to learn the concurrency the hard way, not just Java, but like using Go or using C to get the feel more into what is concurrent programming. If you like to adventurous enough, go to GPU. That's fully concurrent system. GPU. That's different. That's a bit different concept of concurrency, because it's kind of actually more parallel processing instead of concurrency. Okay, that's it. Thank you. For the next, I think someone from Singapore.
So this will be the last slide.
Maybe the next one, no, maybe more the next year. And for the topics, it's up to you. There are a lot of topics that we never touched. Just in the past, like for example, we have tech talk related to database stories, and also tech talk related to network infrastructure. That we haven't got kind of tech talk in that context. And maybe tech talk about emerging technology. Maybe if anyone of you know about maybe Elixir or whatever, feel free. Because maybe sometimes we have to focus in one technology stack and never the others. Or like using Redis or how we actually implement Redis to help our reporting so on. Yeah. Waiting for it. So Excel. Yeah.
I want to ask a question. just what's up. I just joined Friday.
Yeah.
So yeah, I've already so
Yeah.
I need to set up the framework for the testing and all those stuff. So I just wanted to know like how you do the because right now what I do is the road testing and I use JMeter for that to trigger the numbers and all those stuff. So what's the approach you are doing for that?
Actually, for now, we are doing C testing only for kind of unit test.
Okay,
Not
okay.
for the big region.
Okay.
So if there is a core functionality on the framework that you like test, like on the unit
Okay.
or the unit, we simply spawn multiple
Okay.
layers
Okay.
and then try to run it into multiple executions.
Okay.
So it's more actually unit testing.
Okay. Got it. Got it.
For the actual integration testing and all, actually,
Yeah, that's what Sudeep said. That's what Sudeep said that. So I just attended today that the Traveloka, what's it called? EA and legal thing.
yeah.
That session was so I just attended that. And meanwhile, I just want to know how the QA are working here. Any automation is happening or something so that I can, because I'm planning to set up there.
I think that's a key challenge because we don't have such thing in place.
Okay.
Except maybe for mobile application. Because for mobile application, as far as I know, maybe we can ask Jamie more about it. Then automation in place. Because very hard to get if you actually mess up with. We can do
That's true. That's true.
So they have a bit strong, but for the backend, actually. Yeah. So, yeah.
There's another meeting happening there.
Yeah.
Oh, okay.